I am here to talk to you today about turbulence and Reynolds number. Turbulence and Reynolds number. Okay, so you've probably also seen this equation or some form of it. So Reynolds number, RE, equals maybe rho V bar D divided by mu. There are a few ways to write this. You may have also seen something along the lines of 2 rho Q R divided by mu A, something like that. Okay, so what this is talking about is turbulence. Turbulence is something that you see when you've got a fluid flowing. It doesn't have to be through a pipe, but we're mostly interested in pipes, and your problems will pretty much all be these circular cross-section cylindrical pipes like this, and you've got some fluid flowing through it this way. Okay, so you've got that going on, and you can sort of have one of two states. You can have some fluid flowing through this way, nice, and this is what we call laminar flow, where it's all flowing in the same direction. Now, turbulent flow is where you've got maybe a little bit flowing sort of like that, but then you've got something going off here and then making a mess, and then this stuff down here is making a mess. So this is laminar down here on this side, and this is turbulent flow. Okay, so this Reynolds number that we're talking about calculating tells you something about whether or not a system is going to be in turbulent flow or in laminar flow. So if the Reynolds number is greater than 2000, you're probably going to have turbulent flow. So turbulent, right? If it's less, probably laminar. So there's a little bit of something called a transition period where you can sort of have mixing where it goes from turbulent to laminar is bouncing around a little bit, but for our purposes the cutoff is 2000. Greater than 2000 turbulent, less than 2000 you got laminar flow, right? Okay, so I haven't explained what all of these numbers mean, right? So let's go back and do that. So let's start with this rho, which I wrote like that. So that is the mass density, and it will have units something like grams per milliliter, right? So mass per unit volume, okay? All right. D here, D is the diameter of the pipe of interest. A is the cross-sectional area, so that could be A, and it's a cylinder, so it's the same A all the way along. R, is just half the diameter there. And some people favor writing it this way, some people favor writing it this way. There are sort of different ways you can think about it. But V bar is the average speed of fluid flowing through this pipe, and the volume flow. So speed, this will be something like meters per second. Oh, that popped up. Meters per second, have units of meters per second, something like that. Volume flow will have something like milliliters per second, right? Because this is a volume divided by unit time. Mu is the viscosity. So viscosity, and this is the thing that's probably a little less familiar to you. So this will have units like centipoise. So the unit of viscosity, this is equal to centipascals times seconds. You don't really need to know that. Just know that centipoise, and really the most important reason that you can know centipoise is for Scrabble. Let's give you water first. So that's about 0.07 C centipoise, right? Okay, so of course this is you're studying for the MCAT, so we're going to give you something about a biological system, blood, very important biological fluid, and honey, not such an important biological fluid, but useful for illustration. So this will be 2,000, let's actually write in all the zeros, 2,000 to 10K, and again, centipoise. Okay, so going back up to this Reynolds number, and why do we care about whether or not blood is turbulent or it's not turbulent? If you've got a fluid flowing through something that's turbulent, there's a lot more resistance. You'll have to put a lot more pressure behind it. That's one thing. The other thing is, if you've got turbulent flow like this, if you've got this sort of messy flow, blood is more likely to start its coagulation cascade. So you're more likely to start getting clots and just nastiness that you would much rather not have. So how can this Reynolds number change in a normal biological system? Really, so you've got a few parameters up here that can change, and for convenience, let's just go with this formulation of the Reynolds number equation. So this isn't going to change very much. The mass density could change some, probably not going to change a whole lot. Velocity can change if your heart starts beating a lot faster, right? So if V goes up, R goes up, the Reynolds number goes up, right? So moving faster, more likely to be turbulent. Okay, so bigger pipe, if you have dilation of the vessel, if this gets bigger, if D gets bigger, more likely to have turbulence, right? If everything else stays the same. All right. The last thing is mu. What happens if the viscosity goes up or down? Just take a minute and think about that. What happens if the viscosity goes down? What happens to the Reynolds number? Okay, let's say for a second that the viscosity goes up. Now, why would the viscosity goes up? Remember, viscosity going up means blood looks more like honey. So you could lose some water. It could start looking less like water, looking more like honey. And the way that you can do that is if you get a little bit dehydrated, you could lose some of the water in your blood through sweat, and you would leave behind all the proteins and all that sort of thing. So you can get this mu going up. If mu goes up here, what happens to the Reynolds number? This denominator gets bigger. This goes down. Reynolds number goes down. You're actually more likely to have laminar flow. You might have some other problems, but you're more likely to have laminar flow. You're less likely to have turbulent flow problems. Now, there are some things that can happen that would make the Reynolds number go up, or the viscosity go down. So how will the viscosity go down? Remember, viscosity going down means the blood is starting to look more like water. Blood looks more like water, gets a little bit thinner. Maybe you have to inject somebody with saline, for instance, so you're diluting their blood, making it look more like water. If this goes down, again, the Reynolds number is going to go up.